thank you very much, David. So I'm very pleased to be here and to have the opportunity to present a few results obtained with the help of my colleague. They will be mentioned later. So mainly about selection bias in machine learning, but there are other related issues, fairness in particular. I'm not sure I will be able to discuss that today. In machine learning, these last decades, we have spent much time in scaling the algorithm to be able to exploit the massive data. But now, many methodological issues remain to make AI system fully acceptable. Robustness, so I'm sure Pablo, for instance, has discussed that in a preliminary talk. Fairness, privacy constraints, explainability, one of the topics of my colleague Florence Dalcher. The frugality of computation, but today I will more focus on reliability issues, in particular on training data representativeness. And this will be the main subject of this talk. And it's also one of the main topics of research program we have with industrial partners. So this industrial chair, AI for industry, we have with Airbus, Renault Ampere, the car manufacturer, and IDEMIA, a company specialized in security systems. And I will use one of their use case to describe recent advances in representativeness of training data for machine learning. So a very hot topic, facial recognition systems, mainly for identity verification. So when you go to the airport, for instance, you show your passport, there is a photo on it, and they take a photo of you after the trip. If you resemble yourself enough, then the door automatically opens. Okay, so it's if you want to design such a system, if you want to do it quick and dirty, for instance, you first train a deep convolutional neural network to classify photos. Typically, you may use photos of celebrities. There are plenty of them on the internet. And you don't use the classifier itself, you just use the last internal layer. This will be your embedding. And by means of this embedding, you're able to compute, for instance, cosine similarity functions. And this will be used to measure the similarity between two photos. Of course, these images, they are of very high dimension, and a similarity scoring function. So that's a function taking positive values defined on the product space of the images by itself. Okay, how do you evaluate such scoring function? In general, by means of a ROC curve, you just plot the false positive rate, false acceptance rates. Because the similarity exceeds some threshold value t, you think that's the same person, but this is not the case. Against the true positive rate, so the same, but here you have a genuine pair. Okay, so the FAR against the TAR. Okay. There are also variants, and you are interested in various functioning points. Typically, you set the FAR around 10 to the power minus 3, something like this. Okay, but the whole curve itself is of interest. So this is the performance measure. And how do you use this to assess empirically the performance of a face recognition system? You just replace these conditional probabilities by their empirical version. Okay. So they could be rather complex. So in general, you have access to a public database with many images of the same person, and you compute the frequencies, estimating the conditional probabilities. In general, because it's a pairwise problem, they're in the form of multi or one sample U statistics, ratios of such functionals. And so it can be studied. Such curves could be optimized, but that's not really the subject of the present talk. The question is, what do they exactly represent? Because the acquisition process, this public database, nothing is controlled at all. So in general, depending on the public database chosen, the performance may vary significantly. This is very well documented. I mentioned celebrity databases. They are not representative of the population at the airport or at border controls, of course. It's well known that, for instance, Caucasian people are overrepresented in such. And so there is no reliable measure of performance. And these photos that are publicly available, they also they go also with additional features. So it could be about the individual itself, him or herself, woman, man, young, old. But it can be also the additional feature. They can also describe the background or the level of resolution of the image. So we have auxiliary information, but there is a representativeness issue. Okay, and so what happens is that the promised performance after the training stage, it's very different from the error made during the deployment of the system. And there is no surprise, that's very common in machine learning. The training data set has not the same distribution as the test data set, the data we have during the test phase. So that's a very difficult question, especially because these distributions, they are defined on very high dimensional spaces. So the question is to be able to assess the difference, to understand it, so regarding which features, for instance, which segment of population is over or underrepresented, and also can the shift in population be corrected. So that's one of the main. So there is some representativeness issue, but there are also other problems. So generically, it's called bias in AI systems, but we are familiar with selection bias in statistics, for instance. That's another type of bias that is of interest also in facial recognition systems. But this type of bias is actually fairness. The problem is that the ROC curves, their shape, their form, can vary much depending on the segment of population of interest. Or it could be a desirable objective to have some equal treatment across all the sensitive groups. For instance, what is true is that the systems, they usually work better for a white male than for other segment of the population. And sometimes what is the possible cause for that is the fact that certain segments of the populations, they are really underrepresented. But that's not necessarily the main explanation for the disparities we see in the ROC curves. So for instance, these ROC curves, they are publicly available on the NIST website, the website of American Regulatory Institute.
but this is very common in machine learning. Many types of bias are combined. So of course, we have a finite number of training examples, so we have sampling bias. But as I said, we have also selection bias. Some types of data are more frequently observed. Of course, we have model bias. I've mentioned some deep CNN to design AI systems. And of course, it has its own merits and drawbacks. But in machine learning, people are familiar with data challenge procedures. So they compare usually many types of predictive models. But you have also the intrinsic difficulty of a problem. For instance, if you try to recognize the identity of newborns, that's way more difficult. This is well known. And the question is it possible to equalize performance without degrading some errors? So our agenda today is to take a deeper look at selection bias mitigation in machine learning. So essentially, the theory assumes that training data, they are independent copies of some generic random variable, but that's not true in practice. So the first question I will deal with is it possible to train based on dependent data? If you select yourself the data for learning, so you incorporate some dependent structure, are the guarantees still valid? And when there is absolutely no control of sampling, is it possible to mitigate the selection bias using as well high-dimensional statistical learning techniques in the fashion of post-calibration in survey sampling? If time permits, I will also show some a demonstration of software we develop at Telecom that automatically quantifies selection bias in data. It has also interpretability properties, and if I have time, I will explain the theory behind that. But that's not the main purpose of the talk. So I will deal with a simpler problem than the ROC curve optimization problem. The simplest problem actually in machine learning, the binary classification problem. So just to explain the main ideas behind selection bias and its mitigation. So in binary classification, we have a binary label y, and we also observe some input information possibly useful to predict the label x. So in general, it's a very high-dimensional vector. So of course, there is a best way to predict y based on x. That's the Bayes classifier. Of course, if you have some level set of a posterior probability, eta of x, you know how to predict best. So this is extremely classic. So that's the solution, this Bayes classifier of classification error. So the probability related to the distribution, to the unknown distribution of the pair xy. So of course, we don't know this probability. So the main paradigm of machine learning is empirical risk minimization. You just replace the probability by its empirical version. It can be a smoothed or penalized version. Okay, and you minimize the statistical version of it over some class, large J, of classifiers. Okay, and you can control, of course, the excess of risk, so the risk of your empirical minimizer minus the true minimum. So classically, it can be divided in two terms. On the right, the bias term, so depending on the richness of a class large J. If it contains, of course, the Bayes classifier is 0, and the stochastic term, the maximal deviation over the class of between the empirical risk and its true version. And you can control this by means of concentration inequalities for empirical processes, standard averages indexed by classes of functions or sets. For instance, you may use the McDermott inequality or Talleyrand inequality combined with complexity assumptions for the class of classifiers. VC inequality, for instance, and you recover the universal rate 1 over square root of n, that of the CLT, of course. So, and it works perfectly well, provided you are able to solve the optimization problem, and you have enough training examples with a good distribution. Okay. So this is behind the current success of many AI applications. But a crucial hypothesis is that the training data, they have the same distribution as the data during the predictive phase. And that's a very difficult problem to test whether two high-dimensional data sets have the same distribution. This can be perfectly solved in one dimension. And so certainly if you avoid making parametric assumptions on the distributions, the best way to do this is to apply rank tests. Okay, they have optimality properties. They are able to distinguish, to detect alternatives very close to the null assumption. And recently we have developed, so of course you can use probability metrics, and possibly based on optimal transport. There are many ways of quantifying the distance between two probability distributions. But the problem is that in general, you don't know at all the distribution of the distance, its empirical version, under the null assumption. Okay, you can approximate it using some central limit theorem or something like this, but you don't know it, and there is a significant bias. But if you look at ranks, for instance, ranks under the null assumption, you know their distribution. They are uniformly distributed among all the possible ranks in the pool sample. So if you are able to apply this methodology in a high dimension, if you are able to get the ROC curve corresponding to the two distributions in high dimension, then you can apply rank tests as if you were in the univariate setting. And also, if your ranking rule is interpretable, you may also understand why the two data sets are very different. So if I have time, I will make a demo of this software later. So I go back to the problem of is it possible to apply empirical risk minimization even if the data exhibits some strong dependent structure if you select them by means of certain sampling scheme, survey scheme. And actually, that's what you do when you apply stochastic gradient descent. In general, you choose uniformly at random some mini batch just to be able to compute a statistical version, a scalable statistical version of a gradient. And this is behind the Spark technology, for instance. But it was mainly for scalability issues that it has been studied. But is it apart from scalability issues, is it better to pick your subsample yourself based on the auxiliary information features you have on the data? So I will call them the WIs, for instance. And is there a better way to choose your subsample? And will you have some benefit regarding the statistical error? So what is a sampling plan? It's just a probability distribution on the set of all data subsets. Okay. So in general, it's a conditional probability distribution because you choose some observations depending on the auxiliary features. You prefer to choose, I don't know, that image rather than this other image. Okay. So it can be rather complicated, but the classical sampling plans The simplest certainly is the Poisson plan, or it's just the fact, the event that one observation is selected or not. These events, they are completely independent. You can also control the size of a subsample S you get. This is the case where you consider random sampling without replacement. Okay, but in that case, directly you introduce some dependent structure. Okay, if epsilon I is the indicator function that observation I has been selected, of course, the size of a sample is the sum of the epsilon i's. Okay. So in general, you just to make computations, statistical computations, you don't need to describe the whole distribution, but only the inclusion probabilities. So these are the marginals. So pi of I is just the probability that observation I is in your subsample. And you have also the second order inclusion probabilities. Here you're looking at pairs. And of course, if you select yourself by means of a sampling plan your training sample, you shouldn't rely on the raw empirical risk based on that sample. This could be biased, of course. Just take the expectation of that. It's not a fair estimate. It's not an unbased estimate of the risk. Okay, so you have to apply some very old trick in statistics, inverse probability weighting, of course. So in the case of in survey theory, this is simply called Horvitz-Thompson estimator. Okay, so you divide by the probability of being observed here, pi I, probability that observation I lies in your training data set. So you can form some unbiased estimate of the empirical risk by means of it, and what you should minimize is this empirical risk estimate over your class. Okay, so first, I've said nothing about the way you construct your inclusion probabilities. So in general, as argument, you have the auxiliary information that is available. And what you should control also in general, in particular, if your machine algorithm needs to scale up well, it's the size of training data set, the size of a subsample. So typically, you have to standardize your inclusion probabilities so that the sum of the pi i's equal to small n, which is in general much smaller than the whole data set. And this is very akin to propensity scores, very classic in causal inference. In general, it could be modeled using logistic regression in the simplest case, but also you can use other classifiers, neural networks, and so on and so forth. So first, what you have to see is that it's not easy to extend the empirical risk minimization theory to this kind of risk functional, simply because of the dependent structure you have incorporated. If you have chosen this observation rather than this other observation, you have some dependent structure that cannot be handled easily. Okay? Except, of course, if the sampling scheme is a Poisson scheme. Okay? Because here you have independence and you can apply the non-asymptotic theory of independent averages. So what can you do? Fortunately, just like sampling without replacements, many survey plans, they are negatively associated. I mean, the indicator function, the epsilon i's, they are negatively associated. And if you have that property, then you can show that it works. I can say a word about that. So some survey schemes are not exactly negatively associated, but they can be tightly coupled with negatively associated plans. So there is some hope to say something about the validity of machine learning, empirical risk minimization, when you apply this to training data sets obtained by means of a survey plan. So what is this is negative association. This is the classic property. Okay, so you have this negative covariance, and by means of that property, you can make the classic Chernoff trick. So what is underlying most concentration inequalities work, and you get exactly the same bound as if there were no dependence at all. Okay, so you recover the same guarantees as if there were completely independent, as for the Poisson case. But to tell the truth, if you use some survey sampling scheme, is to get a better estimation. It's not just to do as and what makes a survey scheme relevant is its ability to reduce the conditional variance. Okay. So you want, in general, a bound that is way better than this bound here. I don't know. I can show it. No, sorry, it doesn't work. The bound in the middle of a slide. So it's possible to refine the concentration inequalities, but for instance, for rejective sampling, with my colleague Patrice Bertaille, we have shown that it's possible to get a Bernstein type inequalities incorporating the reduced variance of a rejective sample. You just have to write the complex sampling distribution. So it's as a conditional distribution of a Poisson scheme. So a rejective scheme is simply a Poisson scheme condition upon its size. Okay. So if you want to sample with unequal probabilities, but control the size of your training data sets, okay, you can sample using a Poisson scheme, but just keep the data sets that with the desired size, small n, for instance. So if you write the distribution like this, of course your probabilities, they will become ratios of probabilities. This is just and if you're able to control the ratio, then it's possible to get very sharp concentration inequalities. So we have done this first for rejective sampling, and now this has been recently extended to general negatively associated survey schemes. The goal is to incorporate the reduced variance properties in the description of generalization bounds. And it works very well in practice. If you choose your subsample for stochastic gradient descent by means of an appropriate sampling scheme with appropriate inclusion probability weights. Here you have the optimal weights, for instance, so as to minimize the asymptotic variance of your stochastic gradient descent compared to uniform sampling without replacements. There is a huge difference. Okay, so just know that there is some theory saying that if you choose your training examples by means of a sampling scheme, it works. This is theoretically valid in many situations, and in practice, it improves, it speeds up the algorithm. But what if the inclusion probabilities are unknown? Okay, if you don't know them, for instance, you have biased data. Okay, it's not yourself who have chosen the data, you just have data. And that's the case in the public data sets I've mentioned. People have chosen to share their images, their photos. We know nothing in general about the biasing mechanism. Of course, if you know nothing about the biasing mechanism, that's hopeless. Okay. If you know something about the biasing mechanism, maybe there is some hope, but that's what we tried to discover. So we have started to study two types of biasing mechanism. First, random censoring. Machine learning does the empirical risk minimization principle still work. And also selection bias models in the spirit of what has done Vardy in the mid-80s, but for statistical inference in an asymptotic setting. Okay, so you have data and you know that they are randomly censored. Okay, so of course you shouldn't apply empirical risk minimization based on the raw data set. Otherwise, for instance, if it's a right censoring, you would underestimate the length, the duration you want to predict. So here I have switched to regression, but it's very akin to classification. That's the same kind of problem. Ideally, we would minimize some empirical average, but here we have not the complete data, we have the censored data. But you can rewrite the quadratic risk by means of a survivor function of censoring variable C. So this is extremely classic. Okay, the problem is that in general you don't know the survivor function of this censoring random variable, but you can estimate it. So in general, in the study of durations, that's the length of the duration of interest that that is studied. But here, what matters is the survivor function of the censoring variable. So you can replace it by a classic Kaplan-Meier estimator and plug it in the risk functional. So of course, the risk functional now is way more complicated, but it's not at all an empirical process. But you can, if you are patient enough, you can linearize it and study its fluctuations by means of U-process theory. Okay, and just like for the use of sampling scheme, you recover nearly the same learning rate as in absence of bias. Okay. That's noticeable. And this work, of course, due to the denominator, you have some instability, of course, but it works theoretically and empirically. Another situation where you know something about the biasing mechanism is the framework proposed by Vardy. So you have several source data sets, D1, DK, each one drawn from some probability distribution P of K that is different from the target distribution or the test distribution P. Okay. So they're absolutely continuous, they're supposedly absolutely continuous with respect to this P or P-test distribution. You know the biasing mechanism, meaning that you know the biasing function small wk, but you don't know the proportion, the fraction it represents in your target population, meaning that you don't know the standardizing factors, large omega k, involved in the assumption here. Okay. So for instance, you know that in your data sets you have only, I don't know, high resolution photos, or you have more, you have twice more photos of male people, for instance, than in your target population. Okay. In general, so these biasing functions, they are indicator functions, but we don't need any smoothness assumptions on them. We assume that we have large K samples that are biased, okay? And of course, we shouldn't treat them as if there was no bias, of course, because the average, the raw empirical distribution is, of course, different unless the omega k's are equal to 1. They are different from the test distribution. Okay. So to be able to recover the distribution P from the biased samples, you need some identifiability assumptions. Of course, if you bind the bias distribution P of K, their supports together, you should be able to reconstitute the whole support of your target distribution. Okay, and you need more than that. You need some overlap, just as in the figure here, so as to be able to reconstruct the target distribution. So P bar here, that's just the average of the PKs. Okay, so of course this is the biased version of target distribution. So you shouldn't rely on this. But if you have this identifiability assumption, then you can write the target distribution as a certain density function times the so you can form the Radon-Nikodym derivative of test distribution with respect to the average distribution. But for this, you need to know the large omega k's. Okay. So the goal is to be able to recover them from the data. So their solutions, what can be shown is that they are solution of a certain nonlinear system, but you can construct some, so this is true if you have this identifiability assumption that is fulfilled. And what should be done, of course, statistically, is to replace this nonlinear system by a statistical version of it, just as in empirical risk minimization. And what you can show is that you can, so it has a unique solution up to certain standardization. And you can recover with high probability the weights WK if you solve this empirical system. Okay. And what you get is that you can completely get rid of the bias. You achieve exactly, though your data sets are biased, you can reach the same universal learning rate as in absence of, as in full absence of sampling bias. Okay, but it works only if you know the biasing functions. Okay. If you don't know them, of course, it cannot work. So is it possible to leverage machine learning to emulate the biasing mechanisms? Of course, this is not possible if you know nothing about the biasing mechanism. Okay? If you have some auxiliary information, then it's possible. Okay? And that was this is done in survey sampling, for instance. Cohorts in general, they are strongly biased, and the idea is to align some marginal constraints so as to weight the cohorts, and in order to to make its empirical distribution close to the desired distribution. But the difference in survey sampling is that we work conditionally upon the statistical population. In machine learning, the goal is to predict well in the future for any other observation in the future. So the goal is to work unconditionally. Okay. So we assume that we have a training data set that is biased. It has some source distribution P of S that is different from the target distribution P of T. Okay. So this can be viewed as a specific transfer learning problem. You have data that are not distributed as you would like. And the idea, just as before, is to solve a certain optimization problem. Okay. But as in all the previous cases, the risk will be a weighted empirical risk. The question is how to choose the weights, small wi's. Okay. And ideally, we would like to choose them so as to get the same kind of non-asymptotic guarantees. To be, in particular, to be able to control the maximal deviations at the order square root of n or plus a possible log term. Okay. Okay. So machine learning, it's a frequentist ID. So we are not creating information, of course. So we have to assume that the source distribution dominates the target distribution. Otherwise, it's hopeless. Otherwise, you have to incorporate some prior knowledge. So if you do this, of course, there is a radon-Nicodim derivative describing the change of measure. And if you knew it, you would apply importance sampling tricks, very classic in statistics. So you knew, in that case, the ideal weights. Okay? And it works, and there are many. Sometimes you can estimate it if you have some sample of target distribution. But here we will assume that is not the case. So we are not able to estimate the radon-Nicodim derivative. Okay? What we have, and for face recognition systems, that's the case, we have some macro information about the target population. For instance, we know the fraction of male people at the airport or other cross moments. We can assume that we know certain moments of the target distribution. Okay. So we shall assume that we have some auxiliary information in the form of such moments. Okay. So the idea is to learn the weights so as to align the moments we form using the bias data with the known moments. Okay. So if you first solve such a minimization problem and next incorporate your weights in the weighted empirical risk minimization problem, then you get some predictive function here encoded by some parameter theta hat of n. Okay. And what you can show is that by doing this, of course, you need some technical assumptions. I will now go into the details, but you recover exactly the same rate as in absence of bias. Okay. So that's possible to leverage old ideas in survey samplings in machine learning. And this works very well, even if you are not very accurate in aligning the moments. Just with some basic information about the target population, even not very accurate, the performance of weighted empirical risk minimization gets rapidly way better, and at least much better, of course, if you are ignoring the bias in your data sets. Okay, sure. It's fixed. It's fixed. It's fixed. Okay, but what happens empirically is that, so in general, so in survey sampling, the cohorts, they are very small size. And if you incorporate too many moments, so this is called post-calibration, okay, rapidly, it's very difficult to find a solution, okay, just to get this quantity close to zero. But here in machine learning, we are not really interested in that. What we are interested in is in the future risk. Okay, so this is never a problem to incorporate too much information. Okay, and also in particular because the data sets in general they are rather large. Okay, so that's a different point of view. The idea here is to use that for prediction. We are not working on conditionally upon the data. We want to get a bound with respect to the true expectation. And so we are not facing the problems we have in classic survey sampling. Sure, sure. In general, it's a prior knowledge. Okay, you know that at the border control, what is confidential is the photos. Okay, so for instance, the company we work with, they have not access to the photos at border controls, of course, but they have statistics about aggregated statistics about the population at the border control or at the airport. Okay. Yes. This is an example because this is the use case, but actually that's very different from the celebrity database they have. So yeah, just in conclusion, do we have some moment to? How many time? I'm done. Okay. So the paper that has been published is when you assume some parametric model for the link function for this optimal way of reweighting the raw empirical moments. But you can get rid of this assumption. So we shall publish soon a paper on this extension. And also in the example I have shown at the beginning, it was about a pairwise problem, similarity scoring problem. And there are also many unexpected phenomena when you deal with pairs, for instance. And this is also the case where you try to extend the results I have shown for classification or regression problems. So expectation with respect to the variable of interest. As soon as your estimates or use statistics, for instance, there you shouldn't sample in a naive way. So, for instance, we have first studied this phenomenon for scalability purposes. So if you want to compute your FAR statistics or FRR, any use statistics, but if you have n data, the number of pairs, it's of order n square. So rapidly, it's computationally a nightmare. So if you want to compute, to get only n pairs, for instance, what you could do is to subsample in your population, square root of n individual observations, and compute all the pairs. It will be of order n. Okay, but if you do this, you destroy completely the accuracy. Okay, the rate in your CLT, for instance, or in your favorite concentration inequality, it's of the order n to the power 1/4. In contrast, if you directly subsample pairs, you choose n pairs at random, you get exactly the same rate as if you had seen all the data. So that's noticeable, okay? And you have exactly the same kind of phenomenon when you use some auxiliary information. What we shall show in a forthcoming paper is that the information should be related to the pairs and not to the individual observations, not to the individual photos. What is very hard, for instance, you should put more weight in the estimations of the risk in certain duels. I don't know, young male against young woman, for instance. The auxiliary information shouldn't be related to the individuals, should be related to the pairs. And this will permit to drastically also reduce the variance. This is a work in progress, but that's key in the use case I have mentioned. So these are some recent or less recent references about this whole work. So this is still in progress. So I don't know how to proceed. If you have questions, I can answer them, but I can also tell more about the two sample problem in high dimension I have rapidly discussed as you want. Okay. Sure. Sure.
What discrepancies can you handle within this framework? So, for instance, a lot of data sets have biased labels. Right? So it's not a matter of you have underrepresented right? It is more of there is a systematic bias in the way that the data was labeled. If that makes sense. So
sure.
You handle that.
Sure.
Yeah.
No problem. So that's in that case, in general, this shift can be completely easily handled because, for instance, if you have unbalanced populations, that's very classic. You can rewrite, and if you're able to estimate the proportions, there is no problem to correct this kind of bias. Here, this is much more general, and of course, this includes this situation. Yes, because it's about the whole pair, XY, for instance. The shift in population can be related to the whole pair, not necessarily about the input information. Okay, it's what you need is so either you need to know certain thing about the biasing mechanism. Okay, so in that case, if you know something that is very specific, you can mimic, you can estimate the weights. So that was the case in sensoring or with Vardy, which of course incorporate the setting you mentioned. Okay, but if you know nothing about the biased individuals, you need to know something about, you need to have some macro information about the target population. Okay, so that's, and that's realistic in, but if you know nothing, of course, there is no hope. So either it's in the form of a prior knowledge, or else it's something about the data themselves. Oops. So I have been very brief about this the two-sample problem and our ability to detect differences between two high-dimensional populations, particular populations of photos, for instance. We are currently developing a software in particular, and we are able to apply it to face image data sets, but any kind of data. It could be text or graphs or anything that is of high dimension. So, and that's certainly the beginning of the story. First, if you want to mitigate selection bias, you have to compare populations. And this will be also this is one of the main subject of AI regulation. So they care about the representativeness of training examples that are feeding the AI systems. But it's very difficult to check whether the training data are distributed as the data you will see in the predictive phase, and how to do this from an operation. So as I said rapidly, in the unidimensional case, that's very simple. Okay, you just you have two populations, the green one and the blue one here, and of course you could apply some classic parametric test if you assume some parametric assumption, Gaussian hypothesis, for instance. But if, for instance, your distribution are really multimodal and you want to avoid parametric modeling, as I said, the best way, so it's a very old idea, is to deal with ranks. Okay, so it has been introduced by Spearman more than 1 century ago. You just look at the ranks of the green population among the pooled population. And so a classic test is the rank sum test, called also the Mann-Whitney-Wilcoxon test. Okay, you just look at the sum of the ranks of the greens, for instance. Okay, and under the null assumption, under the assumption that the green points are distributed as the blue points, we know this is tabulated. We know the distribution of this statistic, because of course the ranks, they should be uniformly distributed over the whole population of ranks. And there are many, of course, variants of these rank test statistics. So there is a whole theory due to Hayek in particular, depending on the way this distribution differ, you are able to detect the small difference by means of certain rank test statistics. So in general, they are indexed by, they are defined by means of score generating functions, and they have this form. Okay, and so this is well known that for contiguous alternatives, they have asymptotic optimality properties. For instance, a simple shift in distribution translation Mann-Whitney-Wilcoxon is proved to be asymptotically optimal. And it's possible, of course, to develop a non-asymptotic or asymptotic theory, because as I said, the ranks, they can be linearized, and if you're patient enough, you're able to study them precisely. And when you have a test, procedure, of course, in general, you control the type 1 error, the bias, and you try to get the best power. Okay? And there is a very well-known theorem in statistics, the Neyman-Pearson's lemma, claiming that the likelihood ratio test statistics is the optimal one. Okay? It yields a uniformly most powerful test. So and you plot the ROC curve, so the type 1 error against the type 2 error. So that's another ROC curve. We have seen that for as measure of performance of facial recognition systems. Here, the goal is not to use the ROC curve as a performance for the test, but use it as a tool to design a test. Okay, because if you have two probability distribution, a good way of looking at their difference is to draw the probability plot. Okay, if they are the same distribution, so if I know the population of reference is the blue one, you get the diagonal. But as soon, for instance, if you consider another population, the red one, for instance, the ROC curve differs from the diagonal. Okay, and the more difference, the larger the deviation from the diagonal. Okay. And all, so you don't know the ROC curve, so if you have data from the two populations, you can compute some empirical version. And actually, any rank statistic is a byproduct of this empirical ROC curve. Okay. And what is good is that the empirical ROC curve, you can plot them in the, of course, directly in the univariate case. Okay, you know its distribution, so it's a function, random function, but you know its distribution under the null assumption. Okay, and for instance, the Mann-Whitney-Wilcoxon, that's just the area under the ROC curve. So it's equal to 1/2 if the two distributions are the same. Okay, and also the AUC, okay, minus 1/2, it can also be seen as some probability matrix between the two distributions. You can rewrite that in a form that is akin to the Mallows of the L1 Wasserstein distance, for instance. So it's a natural way of quantifying the PP plot is a natural way of quantifying the difference between two distributions. Okay, so this is a good way to look at differences. So what we have developed, so just I'll be very brief, is to a software that extends this approach to high-dimensional data sets. The idea is to solve some ranking problem. So you have your two populations, and of course, you want to get some scoring function, just as the similarity scoring function we have seen. But the idea is, so we assign a label to each population, the negative and the positive, for instance. And the idea is to rank the pooled population just like the likelihood ratio would do. Okay, so any increasing transform of likelihood ratio would yield the same optimal ROC curve. So if you're able to, by means of a machine learning program, to recover the best optimal ROC curve, you're able to quantify the difference between the two distributions. So how do you quantify, how do you extend the univariate distribution? So you just solve the bipartite correcting problem. So you get some empirical, some ROC curve estimate. So it means that by means of this scoring function, the scoring function you have learned, you're able to rank your data, and you apply any rank test to this univariate data, the data you have projected onto the real line. There are alternatives of that. For instance, my colleague Pavlo, he works on a depth function, but he gives himself a priori the form of the projection. Here, the idea is to learn the way, is to learn how to project non-parametrically. Okay, so you try to project best by optimizing the ROC curve, and once you have done this, you know how to project the data, and you know how to see optimally the differences between the two samples. Okay, and what is important is that because you are dealing with ranks now, you know you are able to compute the p-value. You are able to assign a probability of the absence of bias assumption. Okay. So if you know how to solve ROC optimization, you know how to test equality in distribution for high-dimensional data. And if your projection, if your scoring function is itself interpretable, you know, for instance, which features are responsible for the difference. You discover, if you cross, for instance, age and gender, for instance, you observe that the two populations, they are different. You're able to get the arguments of your link function in the bias mitigation I have mentioned before, so as to solve the difficulties. So this is now software. So you can look at the demo we have, and now we are collaborating with our industrial partners to make this fully operational and to work with the images I have mentioned. That's all. It's learned. It's learned. So I have not said much about that because so I have worked much on ROC curve optimization. So the problem is that so you have two populations and you want to find the scoring function which yields the highest ROC curve. And as I said, with Neyman Pearson, we know that this is the likelihood or any increasing transform of it. So the goal is not to recover the Radon-Nikodym derivative between the two distributions, is to find any increasing transform of it. Okay, so it's much simpler. And so I have developed an algorithm that optimizes everywhere that curve. So it's a statistical version of a finite element method. The idea, of course, is to discretize the problem. If you want to get an order, for instance, you can see that. So the idea is the larger the score, the higher the probability to be to have label 1, for instance, to be from one certain population, one certain distribution. Okay, so when you apply some classification method, you just recover the likeliest label. But when you want to get an order, it's much worse than that. You want to get, for instance, the first best 1%, the best 2%, the best 3%. It's a nested collection of classification problems. And each point of the ROC curve corresponds to a solution of a certain classification problem, depending on the depending on the class probabilities, as was mentioned just before. So if you know how to discretize the scoring problem, you just apply classification problems in a smart way. You see, tree rank is the simplest version of the algorithm I have developed to optimize everywhere the ROC curve, and the software is completely based on that. So of course, how do you get the scoring functions? How do you get the projection? By learning it. And how do you learn it? By optimizing everywhere the ROC curve. Of course, you have a bias model, but okay, if the bias model and that's the bet behind machine learning. You expect that you have models that are flexible enough so that the bias model is negligible. And of course, in the analysis, because this this has been studied mathematically, this approach, this machine learning approach to the two-sample problem, there is a trade-off between the bias model and other types of sources of error. Okay, but in general, it's a bit hidden in the analysis of machine learning techniques, the bias model, and it's dealt with by means of model selection techniques, or you compare models. Of course, there is some, this is optimal provided that the model bias is, but if your algorithm is flexible enough, you may a bit ignore it. So I have no time to go into the mathematical details, but just know that, of course, this is complementary of what I have said about the bias mitigation. It's bias detection, sampling bias detection. We'll discuss that later. We have time for that, I hope. But of course, this is very close. I have not discussed propensity score matching, but this is quite similar. Your idea is to line the population and to find the weights. But here we propose some nice way to quantify the differences in population by means of this optimal ROC curve, which is unfortunately unknown, but you can recover it by means of an appropriate algorithm. Sure.